Picture a universe where all the stars, planets, and living things originated from nothing. This concept challenges our current understanding and challenges our limits of knowledge. The origins of atoms, the fundamental units of matter, are central to this great mystery. However, if atoms originated from nothing, then what created this nothing? This question combines scientific and philosophical perspectives, prompting us to reevaluate the meaning of existence. As we delve into the realm of nothingness and the origins of atoms, we embark on a journey that could transform our perception of the universe. Atoms, the basic building blocks of matter, are the essence of the physical universe. From the air we breathe to the stars that light up the night sky, everything we see, touch, and experience is made up of atoms. From the smallest unit of an element that retains its properties to the formation of atoms, an understanding of the universe and our place in it is essential. An atom is defined by its number of protons. For example, hydrogen, the most common and basic element in the universe, has 1 proton. The structure of atoms is controlled by fundamental forces. The strong nuclear force binds the neutrons and protons together in the nucleus, while the weak nuclear force overcomes the repulsive force between the positively charged protons. The atomic cloud is surrounded by negatively charged electrons. Atoms are stable building blocks of matter because of the interplay between the electromagnetic force and the nucleus, which keeps electrons in their orbits. The Big Bang, which created our universe around 138 billion years ago, was a brief period of intense heat and density in the early cosmos, when elementary particles like quarks and gluons were the dominant forces. As the universe cooled and expanded, these particles started to combine. While the early universe supplied the initial batch of light elements, the formation of more complex atoms takes place within the hearts of stars. Nucleosynthesis, the process of proton and neutron formation, occurred within the first few minutes after the Big Bang. During this time, the first atomic nuclei were formed, primarily of hydrogen and helium with trace amounts of lithium and beryllium. Stars are nuclear fusion furnaces that produce helium and other heavy elements like carbon, oxygen, and silicon. As stars evolve, they go through different stages of fusion, producing lighter elements like silicon and carbon, and finally, the heaviest elements like iron when a massive star dies. The energy released during this process powers the star and keeps it glowing. When a star runs out of nuclear fuel, it explodes in a supernova, which releases its enriched material into space and adds heavy elements to the interstellar medium. These remnants can combine to create new stars, planets, and the vast variety of matter we see around us today. Although the processes of atomic formation are crystal clear, the origin of atoms, and by extension, the universe, is still a huge mystery. Prior to it, these inquiries probe the realms of theoretical physics and cosmology, testing our assumptions about the essence of reality. According to one school of thought, the Big Bang was not the starting point of everything, but rather a transition from an earlier state of existence. Other theories, like the multiverse hypothesis, propose that our universe is just one among many, each with its own unique set of physical laws and characteristics. Under this view, the Big Bang could be an ongoing occurrence, a part of a never-ending cycle of creation and destruction. Another branch of study pertains to the idea of quantum fluctuations at the smallest scales controlled by quantum mechanics. Space is not empty, but rather filled with virtual particles and fluctuations, and some theorists suggest that a quantum fluctuation could have caused the Big Bang, which in turn gave birth to our universe. The search for the nature and origin of atoms is a reflection of human curiosity and our urge to understand them. From the earliest speculations about indivisible particles by ancient Greek philosophers to the most recent groundbreaking work in particle accelerators, the path to discovery has been a long and winding one. However, thanks to quantum mechanics and particle physics, we now understand the complex dance of subatomic particles, and technological marvels like electron microscopes and particle colliders have made it possible to probe the very substance of matter, unveiling the intricate workings of atoms, early atomic models, and quantum mechanics. The quest to comprehend the atom, the basic unit of matter, has been a fascinating and groundbreaking part of scientific history. From the strange, experimental findings of the early 20th century to the advent of quantum mechanics, the development of atomic models exemplifies humanity's incessant quest for knowledge and the dramatic changes in our view of the cosmos in the first modern atomic theory, put out by John Dalton in the early 1800s, postulated that elements were made up of indestructible atoms, with each atom being unique. This laid the framework for subsequent discoveries, but the actual complexity of the atomic structure was not revealed for another century. A major milestone was the 1897 discovery of the electron by J.J. Thomson, whose experiments with cathode rays demonstrated the presence of negatively charged particles considerably smaller than atoms. Ernest Rutherford and his colleagues conducted a groundbreaking experiment in 1911 where they bombarded a thin gold foil with alpha particles and studied the scattering patterns. While most of the particles passed through the foil, a small number were deflected at large angles. This model, which envisioned atoms as spheres of positive charge embedded with negatively charged electrons, was soon shown to be incorrect. Nevertheless, it was a significant step in developing atomic theory. Because of this surprising outcome, Rutherford proposed a new model of atoms in which a small, densely charged nucleus is surrounded by electrons. This model explained a lot, but it also led to new questions since, according to classical physics, electrons in orbit around the nucleus should constantly release radiation, draining energy and then re-entering the nucleus. This paradox established the groundwork for subsequent advances in 1913, a Danish physicist named Niels Bohr, who drew inspiration from quantum theory, presented a revolutionary model that solved the stability problem. Bohr postulated that electrons could only exist in specific quantized orbits around the nucleus, and that they could only move between these orbits by absorbing or emitting photons. This model clarified the spectral lines seen in hydrogen atoms when electrons shifted from one orbit to another. From an elevated to a lower energy state, it released a photon with a wavelength that corresponded to the energy disparity between the two states. This explained the discrete spectral line observed in the emission spectrum of hydrogen. Although B's theory was a giant leap forward, it was not without its flaws. It succeeded admirably with hydrogen, but failed miserably when it came to describing more complicated atoms. Regardless, B's model was instrumental in laying the groundwork for quantum mechanics and had a profound impact on our comprehension of atomic structure. Max Planck's research on black-body radiation and Albert Einstein's explanation of the photoelectric effect introduced the concept of quantization of energy. Planck proposed that energy is emitted or absorbed in discrete units called quanta. Einstein extended this idea to describe the photoelectric effect and other atomic and subatomic phenomena. Quantum mechanics emerged in the early 20th century and completely transformed physics. Experimental confirmation of the wave-particle duality laid the groundwork for quantum mechanics, which owes its existence to the work of scientists like Erwin Schrödinger, who developed the field of wave mechanics and came up with the famous Schrödinger equation, which describes the evolution of a system's quantum state over time, and to the work of scientists like Lou de Broglie, who suggested in 1924 that light is composed of particles or photons, each carrying a quantized amount of energy. In 1927, Heisenberg, another important figure in quantum mechanics, proposed the uncertainty principle. According to this principle, it is impossible to know a particle's exact position and momentum at the same time. This inherent uncertainty stems from the wave-particle duality and severely limits the precision of measurements. By introducing this principle, Heisenberg challenged classical deterministic views and highlighted the probabilistic nature of quantum. Quantum mechanics offered a solid foundation for comprehending atomic structure. According to the Schrödinger equation, scientists can determine the probability distributions of electrons around the nucleus, which they call atomic orbitals. These orbitals explain spaces in space where electrons are, probably provide a more realistic picture of how atoms behave than B's orbits. Quantum mechanics also brought up the idea of electron spin, which is a basic property that impacts how electrons behave in magnetic fields. Wolfgang Paul's Pauli exclusion principle stated that no two electrons in an atom could occupy the same quantum state at the same time. This principle clarified how electrons in different energy levels are organized in the periodic table. The advent of quantum mechanics and the development of early atomic models ushered in a new era of scientific discovery. These breakthroughs not only explained long-lived mysteries, but also paved the way for exciting new fields of study, including quantum chemistry, particle physics, condensed matter physics, and Max Planck's quantization of radiation. The history of modern physics is characterized by groundbreaking discoveries that have revolutionized our knowledge of the universe. A new era of scientific thought was born in the late 19th century when physicists grappled with the black body radiation problem. Max Planck's quantization of radiation was a pivotal breakthrough in this field. It not only established quantum mechanics, but also greatly impacted Niels Bohr's groundbreaking work on atomic structure. Together, their discoveries challenged classical paradigms and revealed the mysterious quantum world, an idealized object that absorbs all radiation and re-emits energy across a range of wavelengths is called a black body. The observed spectrum of black body radiation, particularly at higher frequencies, could not be adequately predicted by classical physics, which was based on Maxwell's equations and thermodynamics. This discrepancy, known as the ultraviolet catastrophe, indicated that classical theories were inadequate. In 1900, a German physicist named Max Planck proposed a groundbreaking solution to this radiation problem. Resolve the. In his groundbreaking work on the photoelectric effect in 1905, Albert Einstein advanced our understanding of light and energy even further. This led to the ultraviolet catastrophe, which was mitigated by limiting the amount of energy that could be emitted at higher frequencies. Aligning theoretical predictions with experimental observations, Planck's work marked the birth of quantum theory, which challenged the classical continuum view of energy, phenomenon where light hitting a material surface ejects electrons from that surface. The photoelectric effect is characterized by the immediate ejection of electrons and their dependence on light frequency. A radical departure from classical wave theory, Einstein proposed that light is quantized into discrete particles, later called photons, each carrying a quantum of energy E equals hv. This particle nature of light provided. Niels Bohr, a Danish physicist, was profoundly affected by the developing quantum theories of Planck and Einstein. In 1913, Bohm applied the notion of quantization to the structure of the atom, creating a model that resolved multiple contradictions in atomic theory. Bohm suggested that electrons orbit the nucleus. Einstein was awarded the Nobel Prize in Physics in 1921 for his work on the photoelectric effect, which solidified the concept of quantization in the budding discipline of quantum mechanics. B's model eloquently explains the discrete spectral lines seen in hydrogen's emission spectrum, where electrons jump between quantized energy levels instead of the arbitrary paths proposed by classical physics. Instead of radiating energy, an electron in a given orbit only emits or absorbs energy when transitioning between these quantized orbits. The energy difference between these orbits corresponds to the energy of the emitted or absorbed photon. Levels of photons with specific energies that can be emitted or absorbed. B's theory explained atomic stability, solving the paradox of why electrons do not spiral into the nucleus, as classical physics predicted. The most basic atom, hydrogen, with only one electron, served as a critical test bed for B's model. Quantized orbits, proposed by Max Planck, explained a series of lines in the hydrogen spectrum called the Balmer series, which classical physics had failed to explain. In the process of developing his atomic model, B relied on Planck's quantization principle for theoretical support, which allowed him to explain atomic stability and the discrete nature of atomic spectra. Without Planck's groundbreaking work, B would not have been able to arrive at his groundbreaking model that combined classical and quantum physics. Together, Planck and B's contributions enhanced our comprehension of the microscopic world. Planck's quantization of radiation also resolved the black body radiation problem and introduced the In the 1920s and 1930s, pioneers like Vera worked to lay the groundwork for quantum mechanics, a theory that would transform science and technology in the 20th century. Planck's theoretical framework and B's atomic model, which combined the idea of discrete energy levels with quantization, allowed for a unified explanation of atomic spectra and stability. Modern understanding of atomic and subatomic phenomena is largely due to the work of Heisenberg, Erwin Schrödinger, and Paul Dürr, who built on Planck's principles and developed the Schrödinger equation. Planck's quantization and B's atomic model have left an indelible mark on many disciplines, including chemistry, materials science, information technology, and quantum computing. The development of advanced atomic theory has been characterized by the ongoing evolution and refinement of atomic models. From the early 20th century discoveries that sparked the quantum revolution to the sophisticated models of today, our understanding of atomic structure has deepened, unveiling the intricate and fascinating behavior of electrons. Technological advancements like MRI machines, lasers, and transistors have had a profound impact on modern life. In the beginning, there were models like Dalton's solid sphere and Thomson's plum pudding. Later on, Rutherford's nuclear model introduced the idea of a dense nucleus surrounded by electrons. However, it wasn't until 1913 that Niels Bohr's model included quantization, which is a breakthrough in explaining atomic stability and spectral lines. Unfortunately, Bohr's model, which showed electrons in fixed orbits around the nucleus, was soon found to be inadequate. It could correctly describe the hydrogen atom, but it couldn't. Applied to increasingly complicated atoms, the search for a more all-encompassing theory gave rise to quantum mechanics, which radically transformed our knowledge of atomic structure. One of the most groundbreaking concepts introduced by quantum mechanics is the wave-particle duality of electrons. This idea was put forth by Louis de Broglie in 1924, implying that particles like electrons display both wave-like and particle-like characteristics. At first, experimental evidence was skeptical of de Broglie's hypothesis, but a paradigm shift in our understanding of atomic and subatomic particles occurred when Erwin Schrödinger built on Vogel's hypothesis and performed the famous double-slit experiment with electrons, which proved this dual nature. In this experiment, electrons were fired at a barrier with two slits, and the interference pattern they produced was more reminiscent of waves than particles. The Schrödinger equation, which describes the evolution of a physical system's quantum state over time, was first proposed in 1926. It provided the mathematical framework for understanding the wave-like behavior of electrons, which are treated as standing waves or wave functions around the nucleus. Instead of being in fixed orbits like in Borel's model, these wave functions, denoted by the Greek letter psi, represent the probability distributions of finding an electron in a particular region of space. These quantum numbers define the unique state of an electron in an atom and allow for the detailed configuration of electrons in multi-electron atoms. The solutions to the Schrödinger equation for the hydrogen atom showed that these numbers corresponded to different properties of the electron orbitals. The Pauli exclusion principle, developed by Wolfgang, states that no two electrons in an atom can have the same set of quantum numbers. The concept of standing wave patterns is essential for comprehending electron orbitals and their arrangement in the atomic structure. In classical physics, a standing wave is defined as a wave that stays in the same place with nodes at zero amplitude and antinodes at maximum amplitude. In quantum mechanics, standing wave patterns describe the possible electron states within an atom. The search for the universe's origin is Science has embarked on a remarkable journey, pushing the limits of what we know. At its core, this journey revolves around the Big Bang Theory, the most popular theory explaining how the universe came to be and how the first atoms were formed. Following this narrative, we will travel through time, beginning with the singularity, the inflationary epoch, the formation of stable atoms, and the evolution of the cosmos. Around 138 billion years ago, all the matter and energy that would later form the universe was contained in a singularity. Belgian priest and physicist George proposed the Big Bang Theory in the 1920s, and observational evidence, such as the discovery of cosmic microwave background radiation and the expansion of the universe observed by Edwin Hubble, later provided support for it. The Planck epoch marks the beginning of time, a period so brief that our present-day physical theories are unable to completely explicate it. In this epoch, the four forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were believed to have been unified. The universe was at an unfathomably high temperature and was a boiling sea of energy. As the cosmos cooled and expanded, it entered the grand unification epoch, when gravity separated from the other three forces. At this time, the strong nuclear force remained united with the electroweak force, which is a hybrid of the electromagnetic and weak nuclear forces. The epoch culminated in the dissolution of the strong nuclear force. Among the most important stages of the early cosmos is the inflationary epoch, postulated by Alan Guth in the 1980s. According to cosmic inflation theory, the universe expanded exponentially, increasing in size by a factor of at least 10,261 zero circumflex 26126 in a fraction of a second. This fast expansion eliminated any imperfections, resulting in the homogeneous and isotropic universe that we see today. The cosmic web, galaxies, clusters of galaxies, and other large-scale structures were formed from cosmic fluctuations that were stretched to macroscopic scales during inflation. As the universe cooled and continued to expand, the weak electromagnetic force separated into the electromagnetic and weak nuclear forces. This period is also characterized by the formation of the Higgs field, which provided mass to elementary particles through the Higgs mechanism. As the universe cooled further, it entered. When the universe cooled to below 1 trillion degrees Kelvin, the quarks started to combine to form protons and neutrons. This transition marked the beginning of the Hadron epoch, as most of the antimatter annihilated with matter during this time, leaving a slight excess of matter that would become the building blocks of the universe. During the quark epoch, the temperature was still too high for this to happen. After the Hadron epoch, the cosmos entered the lepton epoch, when leptons like electrons and antileptons made up the vast majority of the universe's mass. However, as the cosmos cooled, these particles started to destroy each other, leaving behind a small surplus of electrons and other leptons. After the lepton epoch, photons took center stage, but since the cosmos was still too hot for electrons to combine with protons to form neutral atoms, a phenomenon called Thomson scattering, photons continued to disperse free electrons. The first stable atoms were formed during this era, when the universe cooled enough for protons and electrons to combine, creating neutral hydrogen atoms through a process called recombination. The decoupling of matter and radiation occurred when photons could travel freely without scattering, resulting in the formation of the cosmic microwave background. Around 100 million years after the Big Bang, regions with slightly higher densities started to collapse under their own gravity, forming the first stars known as population 3 stars. These massive, short-lived stars were responsible for the radiation background, a faint afterglow of the Big Bang, and the subsequent Dark Ages, during which the universe was mostly composed of neutral hydrogen and helium atoms without any sources of light. The first stars and galaxies died out in supernova explosions, loading the cosmos with heavier elements and paving the way for new star and galaxy formation. The radiation from these early stars and galaxies reionized the neutral hydrogen, putting an end to the Dark Ages and making the cosmos transparent to ultraviolet light. This process, called the epoch of reionization, was essential for the development of massive structures. The cosmos is made up of subatomic particles that make up all matter in the universe and are subject to a set of fundamental forces. Over the next billions of years, gravity kept pulling matter together, creating bigger and more complicated structures like galaxies merging into clusters and superclusters, which is what we call the cosmic web. Dark energy is driving the expansion of the universe, which is shaping its future. This narrative delves into the four fundamental forces: gravity, weak force, electromagnetism, and strong force, and the subatomic particles that drive them. Understanding the interplay between these forces is essential for understanding the universe at large, from the tiniest scales of particle physics to the grand structure of galaxies. Isaac Newton's law of universal gravitation, and later refined by Albert Einstein's theory of general relativity, describe how, across infinite distances, the universe's large-scale structure is shaped by gravity. However, Einstein's theory completely changed our understanding of gravity when he described it as a curvature of space-time chaos caused by mass and energy rather than a force. This led to the creation of gravitational wells, into which other objects fall, regardless of their mass. Electromagnetism unites electricity and magnetism into a single theory. It is responsible for the behavior of electrons and atoms, the transmission of light, and the forces between magnets. Unlike gravity, which is weak and affects the entire cosmos, electromagnetism is much stronger and operates between charged particles, as described by James Clerk Maxwell's equations. The electromagnetic force controls a vast array of phenomena, from the chemical bonds that keep molecules together to technological advancements that allow for communication and power generation. It is stronger than gravity, but weaker than electromagnetism and the strong nuclear force. And it operates over infinite distances, though its strength decreases as the square of the distance between charges increases. The weak interaction, which operates at a scale of 10 to the power of minus 18 m and influences subatomic particles like quarks and leptons through the exchange of much heavier W and Z bosons, is essential for star element synthesis and the balance of particles in the universe. It plays a pivotal role in the processes that fuel the sun and other stars. At the same scale, the strong nuclear force, also known as the strong interaction, is the most powerful of the fundamental forces at work at. The strong nuclear force, which overcomes the electromagnetic repulsion between positively charged protons, is responsible for binding protons and neutrons together in atomic nuclei. This interaction is described by the theory of quantum chromodynamics, QCD, which explains how gluons hold quarks together to form protons, neutrons, and other hadrons. The range of this force is extremely short, about 10 to the power of 5 m. The strong force acts over short distances to hold protons and neutrons tightly together. This force is not constant, but increases as quarks are pulled further apart, a phenomenon known as confinement at very short distances. Without it, the repulsive electromagnetic force between protons would cause nuclei to fly apart. The force binds quarks together to form protons and neutrons, and then these nucleons into nuclei, creating the diverse elements of the periodic table. Nuclear reactions, like fission and fusion, release enormous amounts of energy. In fission, the splitting of heavy nuclei releases a tremendous amount of energy, while fusion, the combination of light nuclei, powers stars and has the potential to provide future energy sources on Earth. Quarks are the fundamental constituents of protons and neutrons. The strong nuclear force is attractive and much stronger than electromagnetic repulsion, which ensures nuclear stability. They are available in 6 different flavors: up, down, charm, strange, top, and bottom. One quark in a proton is an up quark, and one quark in a neutron is a down quark. The quarks are bound together by a strong nuclear force that is mediated by gluons, which are massless particles. Unlike photons and electromagnetism, gluons carry a color charge, which leads to a complex interaction network described by quantum chromodynamics. This interaction ensures that quarks, unlike protons, neutrons, and other hadrons, are never found in a state of complete isolation, a feature known as confinement. Instead, they exist in bound states. Quantum chromodynamics, QCD, is the theory that explains the strong interaction. It proposes that quarks have a charge called a color charge, and there are 3 types of gluons, red, green, and blue, that mediate the strong force. The force between quarks is greatest when they are close together, and it grows as they move apart, ensuring that quarks stay. Although quarks have relatively small individual masses, the energy from their strong interaction with hadrons generates most of the mass of proton and neutron nucleons. This shows how the strong force has a profound impact on the material universe. The four fundamental forces and the particles they influence form the basis of the structure and behavior of the universe, and gravity shapes the cosmos on the largest scales. Elements are synthesized through nuclear reactions in stars, which contribute to the balance of matter in the universe, and the stability of atomic nuclei is ensured by the strong nuclear force, which allows for the diversity of elements and the complexity of matter. Electromagnetism governs the motion of galaxies and the formation of cosmological structures, and charged particles are governed by electromagnetism to enable the formation of atoms and molecules that are essential for life. Study of subatomic particles and fundamental forces reveals the complex and interconnected nature of the universe, from the tiniest scales of subatomic particles to the largest cosmic structures. By understanding these components, we can come to terms with the nature of reality, the origins of matter, and the forces that drive the evolution of the cosmos. At ATS, we uncover the fundamental principles that underpin the size and stability of the universe. As we delve deeper into the nature of these forces and particles, we learn about the crucial roles that quarks and gluons, the building blocks of protons and neutrons, interact through the strong force to form atom nuclei. Scientists have long been fascinated by the measurement of atomic and subatomic dimensions, especially when it comes to the size of the universe. Measurements of the proton size have produced conflicting results, challenging our understanding of fundamental physics and prompting a re-examination of established theories. The proton is a fundamental constituent of atomic nuclei. Electron scattering, which involves firing high-energy electrons at protons and analyzing the resulting electromagnetic radiation, is one method for measuring the proton size. Another method is spectroscopy, which involves analyzing the electromagnetic radiation emitted by hydrogen atoms. Spectroscopy, which uses deflection patterns to infer proton size, and inferential methods have traditionally produced consistent results. However, in 2010, a group of researchers using muonic hydrogen, a form of hydrogen in which a much heavier muon replaces the electron, discovered that the proton radius was substantially smaller than earlier measurements. This unexpected finding shook up the field. Known as the proton radius puzzle, has been the subject of much discussion and research. Measurements taken with muonic hydrogen are more accurate than with traditional methods, because the mu orbits the proton closer, amplifying the effects of the proton's charge distribution. However, the discrepancy between the two sets of measurements has not been resolved, and this could indicate either a lack of understanding in quantum electrodynamics or the necessity for new forms of physics that go beyond the standard model. Atoms, the building blocks of matter, have a positively charged nucleus and an electron cloud surrounding it. The forces that hold these components together, known as the nuclear force, are very strong over short distances and serve to counteract the repulsive electromagnetic force between the positively charged protons and electrons. As a result, most atoms stay the same for very long periods of time. Atoms are generally stable, but they can undergo transformations under certain conditions. One popular process that affects atomic stability is radioactive decay, which involves negatively charged electrons being attracted to positively charged protons. This attraction stabilizes the atom by preventing the electrons from drifting away, but the chemical properties of each element are determined by the exact arrangement of electrons around the nucleus, as described by quantum mechanics. Radioactive decay can take many forms, such as alpha decay, beta decay, and gamma decay. Alpha decay, for example, involves the emission of an alpha particle along with 2 protons and 2 neutrons, transforming the original atom into a new element with a lower atomic number. Beta decay, on the other hand, involves the transformation of a neutron into A. The process of radioactive decay includes the release of gamma radiation as a result of an excited nucleus, which can take the form of a proton or vice versa, as well as the emission of a beta particle, an electron, a positron, or a neutrino. A crucial concept in this field is the half-life, or the time it takes for half of the atoms in a radioactive substance sample to decay. Half-life is a statistical measure that reflects the probabilistic nature of decay, as distinct radioactive isotopes decay at random intervals. Atoms and their constituents remain stable over time due to a delicate balance between the forces that hold them together and the processes that can disrupt this equilibrium. For instance, uranium-238 has a half-life of about 45 billion years, making it a useful tool for dating geological formations. The strong nuclear force tightly bonds the protons and neutrons within stable nuclei, and certain isotopes are inherently more stable than others. In addition to natural radioactive decay, human activities can induce nuclear reactions that affect atomic stability. For example, nuclear fission involves the splitting of heavy atomic nuclei into smaller fragments, releasing a substantial amount of energy. This instability leads to radioactive decay, a process that transforms elements and releases energy. This energy has practical applications in fields such as medicine, energy production, and scientific research. In contrast, nuclear fusion, which powers stars by combining lighter nuclei into heavier ones and releasing energy, is a process that scientists are constantly working to harness for energy production. If technological hurdles can be overcome, fusion could provide an endless and clean source of power. The study of atomic stability goes beyond its practical applications to the fundamental understanding of matter and the universe, including the proton radius puzzle. The quest to understand the building blocks of matter drives the dynamic field of scientific inquiry known as the exploration of atomic and subatomic phenomena. Advances in technology, such as particle accelerators and sophisticated detectors, further add to the complexity of subatomic interactions and the limitations of current theories. Resolving this puzzle may require new theoretical frameworks or more precise experimental techniques, which could lead to groundbreaking discoveries in particle physics. Scientists are able to delve further into the mysteries of atomic size and stability, which reminds us of how intricate and interconnected the physical world is. From the puzzling measurements of the proton radius to the profound implications of radioactive decay, these investigations not only expand our knowledge of the microcosm, but also give light on the fundamental principles that shape the macroscopic universe. Interactions and molecular formation. The study of atoms reveals a rich tapestry of phenomena that underlie the structure and behavior of matter. The continuous quest for knowledge in this area promises to reveal new insights and deepen our appreciation of the fundamental forces and particles that make up reality. The diversity and complexity of the material world are underpinned by the formation of molecules, which is a fundamental process. Atoms interact through various mechanisms to form molecules. At the core of molecular formation is the concept of the chemical bond. Chemical bonds are the forces that hold atoms together within a molecule, allowing them to achieve greater stability. There are several types of chemical bonds, each governing specific interactions ruled by the principles of quantum mechanics, electron configurations, and energy states. Chemical bonds are defined by various interactions between the atoms involved and their electrons. A common type of bond is the covalent bond, which happens when two atoms share an electron pair. This makes each atom's electron configuration more stable, similar to the electron configuration of noble gases. For instance, in a water molecule, H2O, each hydrogen atom shares an electron with the oxygen atom, creating a stable arrangement where the oxygen atom has a full outer shell. Depending on a number of shared electron pairs, covalent bonds can be single, double, or triple. Triple bonds involve 3 pairs, while single bonds involve 2 pairs. The strength and length of these bonds vary, with triple bonds being the shortest and strongest, and single bonds being the longest and weakest. Another fundamental type of chemical bond is the ionic bond, which forms when one atom donates an electron to another. Ionic bonds are formed when one atom donates an electron to another, creating an ion with opposite charges. In the case of sodium chloride, for example, the positively charged sodium ion, N+, and a negatively charged chloride ion, Cl, are the products of this process. Metallic bonds are also present in metals, and they are held together by the electrostatic attraction between the ions' opposite charges. Metals' electrical conductivity, malleability, and sea of delocalized electrons are all explained by this type of bonding, which occurs freely throughout the metallic lattice. The formation of chemical bonds is closely related to the energy states of the atoms, as atoms aim to reach a lower state that often corresponds to a more stable configuration. Depending on the nature of the bond, energy is either released or absorbed when atoms form chemical bonds. Interactions like these, where energy is exchanged, play a crucial role in deciding how stable the final molecule will be. In caloric bonding, for example, the shared electrons will be located in molecular orbitals, which are areas in space where the likelihood of finding each other is greatest. These orbitals are formed when atomic orbitals, associated with individual electrons, overlap with one another. As a result, a lower energy state is created, which contributes to the atoms with incomplete outer electron shells, like hydrogen, oxygen, and carbon, are especially prone to forming chemical bonds to achieve a stable electron configuration valence, which is essential for molecular formation and the stability of the molecule. An atom's electron configuration describes the distribution of its electrons among the available energy levels and orbitals. The arrangement of electrons determines how an atom can interact with other atoms and form bonds. Atoms' outermost shell electrons, known as valence electrons, play a crucial role in chemical bonding. The bonding behavior and position of an element in the periodic table are determined by its number of valence electrons. Elements in the same group of the periodic table share similar valence electron configurations and chemical properties. For instance, carbon, which has 4 valence electrons, can form stable octet bonds with other atoms. This tetravalent nature of carbon is the energy states of atoms and molecules are quantized, which means that electrons can only occupy specific levels. When an electron in an atom absorbs energy, it can be excited to a higher level, and when it falls to a lower level, it releases energy, often in the form of light. This principle underpins the enormous diversity of organic compounds, including those that comprise living organisms. Crucial to comprehending chemical reactions and spectroscopy, the interplay between light and matter reveals the energies of electrons in atoms and molecules. Scientists can identify and analyze substances based on their spectral signatures, and molecular formation involves more than just the creation of bonds between atoms. It also involves the resulting molecular geometry, which is influenced by the spatial arrangement of atoms within a molecule and its vapor pair repulsion theory, VPR, is a model for predicting molecular geometry that takes into account the attraction between pairs of electrons in a valence shell. For example, methane, CH4, has a tetrahedral geometry due to the attraction between 4 pairs of bonding electrons surrounding the carbon atom, and water, H2O, has a bench shape due to the attraction between 2 pairs of electrons on the oxygen atom, which causes a nonlinear structure. The unique properties of substances, such as water's height, boiling point, and surface tension dipole, are determined by intermolecular forces, which are forces between molecules. These forces include hydrogen bonding, a strong type of dipole-dipole interaction, and London dispersion forces. Hydrogen bonds to highly electronegative atoms like oxygen, nitrogen, or fluorine. By learning about atomic interactions, chemical bonding, and the impact of electron configurations on energy states, one can gain a full picture of the intermolecular forces at work, including dipole interactions, which involve molecules with permanent dipoles, the positive end of one molecule being drawn to the negative end of another, and London dispersion forces, the weakest of these forces. In the vast expanse of the universe, the behavior of matter can be understood through 2 distinct but interconnected lenses, the macroscopic and the microscopic. The study of atomic and molecular interactions provides insights into the building blocks of matter and the forces that shape the physical world. These principles are essential to chemistry, material science, and the complexities of biological systems. One common analogy compares atoms to tiny solar systems, with electrons orbiting the nucleus much like planets orbit the sun. While this captures the general structure, it falls short in describing the true nature of atomic interactions. Other perspectives allow us to explore and comprehend the complexities of atomic and subatomic behavior, offering insights into the fundamental nature of reality. When it comes to electrons, classical intuition isn't always the best guide. Instead of fixed orbits, electrons exist in regions of space called orbitals, where they are most likely to be found. This cloud-like distribution arises from the wave-like properties of electrons, a concept rooted in quantum mechanics. Another analogy that helps to explain this behavior is thinking of the atom as a cloud. The properties of matter are determined by interactions between atoms. When we touch an object, like a table or a piece of metal, we perceive its solidity. However, this sensation of solidity is an emergent property arising from interactions at the atomic level. Atoms are mostly empty space with a dense nucleus surrounded by a cloud of electrons. The solidity we experience is a result of electromagnetic forces. These interactions, although imperfect, provide a bridge to understanding the seemingly abstract behavior of subatomic particles. The interaction between these electrons is fundamental to the workings of quantum mechanics. For example, when you put your palm against a hard surface, the electrons in your hand will push back against the electrons in the hard surface. This is because, according to the Pauli exclusion principle, no two electrons can occupy the same quantum state at the same time. This principle, in conjunction with the electromagnetic force, prevents the atoms in your hand from penetrating the surface, giving you a feeling of solidity. In addition to the solidity of objects, one of the cornerstones of quantum mechanics is wave-particle duality, which posits that subatomic particles, like electrons, display both wave-like and particle-like characteristics. This duality is essential to comprehending atomic interactions, as electrons in an atom exist in discrete orbitals, each with its own quantized energy level. The chemical bonding of an atom is determined by the configuration of its electrons in its orbitals. Atomic characteristics and interactions, including the formation of chemical bonds when electron clouds overlap, are introduced by quantum mechanics. Another concept introduced by this field is the probability density of electrons, rather than their exact paths, which are described by wave functions. These functions provide the likelihood of an electron being found in a specific region around the nucleus. The electron cloud model is based on this probabilistic nature. The formation of chemical bonds and interactions between atoms are controlled by principles of quantum mechanics. One example is the sharing of electron pairs between atoms. These shared electrons occupy molecular orbitals, which are formed by the overlap of atomic orbitals. The strength and stability of these bonds come from the bottom of the energy state, which is another phenomenon governed by quantum mechanics. The exchange interaction is a quantum effect that is fundamental to comprehending atomic interactions. It is essential for the stability of molecules and materials. The indistinguishability of electrons and their tendency to avoid each other contribute to the overall stability of the atomic arrangement. The solidity of objects at the macroscopic level is the result of the cumulative effect of innumerable atomic interactions. A material's thermal properties are explained by the behavior of its atoms, which are governed by quantum mechanics. Atoms in a solid vibrate around their equilibrium positions, and these vibrations are quantized as phonons. The distribution of these vibrational states determines the material's rigidity, liquidity, and diffusivity, all of which we encounter on a daily basis. The thermal conductivity and specific heat capacity of a material are determined by its quantum mechanical vibrations, which show how quantum mechanics affects macroscopic properties. A material's ability to exhibit zero electrical resistance below a certain temperature is a result of the formation of Cooper pairs, in which electrons move through a pair of holes in the material. Another example of the influence of quantum mechanics on macroscopic behavior is superconductivity. Quantum mechanics offers a framework for understanding the profound interconnectedness of the microscopic and macroscopic worlds, as it leads to the macroscopic property of superconductivity and enables applications like magnetic resonance imaging, MRI, and maglev trains. It also helps us understand atomic and subatomic behavior through analogies, explores touch and interaction at the atomic level and recognizes the role of quantum mechanics in the solidity of objects. Exploring the behavior of atoms, the formation of molecules, and the emergence of material properties, we come across the intriguing concept of color at the atomic level. This color is the result of complex interactions between light, atoms, and molecules, and the laws of reflection, absorption, and thermal radiation. Understanding these interactions is essential for comprehending how matter displays color. At the atomic level, color is strongly related to the electronic structure of atoms and molecules. Electrons in an atom occupy specific positions, and when light interacts with an object, it can be reflected, absorbed, or transmitted, depending on the conditions. The visible spectrum ranges from violet, which has the shortest wavelengths, to red, which has the longest. Quantized energy levels mean that electrons can only exist in specific discrete states. When light hits an atom, it can absorb some of the energy, increasing its energy level. How much energy an atom absorbs depends on the wavelength or color of the light, as well as the specific energy levels of its electrons. Different materials have different sets of energy levels, so they absorb and reflect light differently. For example, a material that one of the most important processes in color perception is reflection. When light hits a surface, some of it is reflected back. The type of reflection depends on the surface's properties at the atomic level. For example, metals have free electrons that can move around and interact with the incident light, so they reflect efficiently. However, substances that absorb most wavelengths, except for red ones, will appear red to the human eye. This is why metals tend to look shiny and reflective. The color of a metal surface is determined by the wavelengths of light that reflect off its surface. On the other hand, nonmetallic surfaces reflect light differently. Light hitting them may only go a short distance before being reflected. This is because the atoms and molecules in nonmetallic materials can interact with light in a way that causes some wavelengths to be absorbed and others to be reflected. The result is that nonmetallic objects can take on a variety of colors and textures. Spectra of different wavelengths of light are attributed to the fact that different substances absorb them. For instance, the pigment melanin in human skin absorbs light of a reddish-brown hue, while chlorophyll in leaves gives them their characteristic green hue. This phenomenon is related to the idea of electronic transitions, which hold that when an atom or molecule absorbs light, it elevates an electron to a higher energy level. Consequently, the energy gap between these levels must equal the energy of the absorbed photon. Thermal radiation is an important part of how atoms and molecules interact with light. As a result of the thermal motion of their molecules and atoms, all objects emit radiation. The wavelength of this radiation depends on the object's temperature. At higher temperatures, objects emit more radiation at shorter wavelengths. For example, a heated iron rod will glow red, orange, and white as its temperature increases. Elevated temperatures are caused by the visible spectrum of electromagnetic radiation emitted by constantly moving atoms and molecules. The wavelength and intensity of this radiation varies with object temperature, with hotter objects emitting more intense, shorter wavelength radiation. Planck's law provides an explanation for the color of an object as a result of thermal radiation by describing the distribution of radiation emitted by a black body at a given temperature can be illustrated by the phenomenon of fluorescence. This is a process wherein a substance absorbs light at one wavelength and then reads it at a longer wavelength. An electron is excited to a higher energy level by the absorbed light, loses some energy through non-radiative processes, and then falls back to a lower energy level, emitting a photon. The emitted light usually has a lower. In fluorescence, the absorbed light is converted into visible light with a shorter wavelength. Phosphorescence, on the other hand, is characterized by a longer time scale for light re-emission. In phosphorescent materials, the absorbed energy can be trapped in a metastable state, which means the material will continue to glow even after the light source is removed. This prolonged emission is caused by the energy being. Glow-in-the-dark materials use this process to gradually release light over time. In addition to these processes, complex optical effects can be created when light interacts with larger structures made of atoms and molecules. For instance, iridescent colors in peacock feathers or a soap bubble are caused by interference and diffraction, which happen when light waves overlap and interact. These effects are not caused by absorption or reflection at the atomic level, but by the specific. The complex interplay between microscopic structures, the effects of specific light wavelengths on those structures, and electromagnetic theory is essential to deciphering atomic-level color perception. The behavior of electrons within atoms and molecules, their light absorption and emission patterns, and their interactions with thermal energy all play a role in the rich tapestry of colors we perceive. Neutron stars and other massive cosmic structures think of a star as one of the most intriguing and extreme objects in the universe. So dense and compact that a sugar cube-sized chunk of its material would weigh about 1,000,000,000 tons on Earth. The microscopic universe of atoms and molecules is responsible for the bright and varied colors that decorate our daily lives. Neutron stars, also known as colossal atomic nuclei due to their dense nucleus of neutrons, form as a result of stellar evolution, the star's life cycle. Under the influence of gravity, a cloud of gas and dust in space, primarily composed of hydrogen, collapses to form a protostar. Once the protostar's core temperature reaches a certain point, nuclear fusion begins, transforming the cloud into a star. Stars produce enormous amounts of energy when hydrogen atoms fuse to form helium. This energy allows stars to shine for millions, if not billions, of years. As the hydrogen in a star's core is depleted, the star undergoes a dramatic change in its life cycle. If the star is large enough, it starts to fuse heavier elements in stages, starting with helium into carbon, and then. The elements undergo a unique process of fusion, which does not generate energy, but instead absorbs it. This process makes the star unstable, and when enough iron builds up in the core, the star can no longer withstand gravity. At this point, a supernova occurs, in which the outer layers of the star are blasted off in a tremendous explosion and the core collapses under the force of gravity. By compressing their protons and electrons in the core, neutrons are created during collapse. This process creates a neutron star, an incredibly dense object composed almost entirely of neutrons. To put it in perspective, a neutron star has approximately 14 times the mass of our Sun, but only around 20 kilometers in diameter. Due to its density, neutron stars are second only to black holes in terms of density in the universe. The conditions inside a neutron star are unlike anything we can encounter on Earth. Neutron stars have atomic structures that are so broken down that they consist of densely packed neutrons instead of atoms. The surface of a neutron star has extremely strong gravity, about 1,000,000,000 times stronger than Earth's. And this enormous gravity also distorts light as it bends around the star, making it appear distorted to an outside observer. One of the most famous behaviors of neutron stars is that they can. When the core of a massive star collapses into a neutron star, it retains most of the angular momentum, but the star spins much faster due to its smaller size. Some neutron stars, called pulsars, emit radiation beams from their magnetic poles as they spin. These beams sweep across space like lighthouse beams. If one of these beams points toward Earth, we could detect it as regular pulses of radio waves, hence the name pulsar. As neutron stars continue to cool, they eventually cool down, fuse, and eventually die. In certain instances, neutron stars can be observed in binary systems, where two stars orbit each other. When a neutron star has a companion star, it can draw matter from its companion, forming a disk of material around the star. This material gets heated and emits X-rays, making these systems very bright in X-ray light. Neutron stars are just a small piece of the larger cosmic tapestry. There are countless other structures like them. Galaxies, for instance, are enormous collections of stars, gas, dust, and dark matter held together by gravity. Our own Milky Way galaxy, for instance, contains hundreds of billions of stars, including our Sun. However, The universe is structured into even larger formations. Galaxies do not tend to be evenly distributed across space. Instead, they tend to cluster together, with each cluster potentially housing hundreds or thousands of galaxies. Cosmic filaments and voids are the biggest structures in the universe. Cosmic filaments are vast thread-like structures made of galaxies and dark matter, and voids are large empty spaces between filaments. By studying neutron stars and these larger cosmic structures, we can learn about the history and evolution of the universe. And because of their extreme conditions, neutron stars provide a natural laboratory for studying physics under conditions that cannot be replicated on. Beyond their scientific significance, neutron stars captivate our imagination. They serve as reminders of the immense cosmic forces and the dramatic outcomes that stars are capable of achieving. The study of neutron stars and the larger structures of the universe is a reflection of human curiosity and our longing to comprehend the universe through space telescopes and other scientific instruments. As we delve deeper into these mysterious objects, we hope to learn more about them and the universe as a whole. As for atoms, the building blocks of matter, they make up everything we see. When scientists study atoms, they find a universe filled with tiny particles in empty spaces. Interestingly, some theories propose that our universe might be structured much like an atom, but on a grander scale. This leads to conversations about the multiverse, which is the idea that our universe could be one of many in a larger system. One theory that compares the universe to an atom comes from the idea of scaling. Atoms have a dense nucleus with protons and neutrons and electrons orbiting around it. If you zoom out far enough, the space between these particles is vast compared to their size. Some scientists imagine that if an atom were scaled up to the size of the universe, it might resemble our own cosmic structure using. While this theory does not imply that atoms and the universe are identical, it does utilize the similarities to help us understand complex concepts. For example, just as atoms are part of larger molecules and structures, some theories suggest that our universe could be a part of a much larger system. Here is where the idea of the multiverse comes into play. According to the multiverse theory, there could exist many universes outside our own, including ones in vast higher dimensional space that we are unable to perceive. Imagine our universe as a bubble floating in a larger space filled with other bubbles, each with its own unique properties. Occasionally, these bubbles might collide or interact in ways we haven't yet discovered. Each universe could have different physical laws, constants, and even different types of atoms. Some universes could be very similar to ours, while others could be completely different. This analogy helps us to think about the multiverse. There are various interpretations of the multiverse theory, with one originating in cosmology, the study of the universe's beginnings and evolution, and one in the inflationary theory, the idea that the universe expanded rapidly immediately following the Big Bang. Some scientists speculate that this inflation may have produced numerous bubble universes, each with its unique set of physical laws. Sourced from string theory, a theoretical framework that attempts to explain all fundamental forces and particles in the universe. Multiverse ideas propose that particles are not point-like, but rather tiny vibrating strings. According to this theory, there could be countless configurations of these strings, which in turn could lead to the possibility of multiple universes, each with its own distinct string configuration. There is a fascinating but highly speculative interpretation of quantum mechanics called the many-world interpretation. According to this view, every time a quantum event occurs, the universe splits into multiple copies, each representing a different outcome. In this view, there could be an almost infinite number of parallel universes, each slightly different from the others. Of course, we don't have direct evidence for the existence of other universes just yet, but the idea of the existence of multiple universes begs the question, what does it mean for our knowledge of the universe and physics in general? In an effort to put this theory to the test, scientists are exploring various avenues, such as the possibility of cosmic microwave background, CMB, variations as a result of potential collisions between our own and other universes. Scientists utilize advanced tools and technologies in their quest to understand atoms, the universe, and the potential multiverse. The theory of the multiverse also intersects with philosophical questions, such as what the implications are for concepts like identity and free will if there are countless other universes with different versions of ourselves. The exploration of these ideas is aided by various technological advancements, such as particle accelerators, supercomputers, and telescopes. For instance, the Large Hadron Collider, LHC, at CERN is among the most powerful instruments for studying the basic properties of particles and forces. Findings from the LHC could shed light on string theory, and by extension, on whether or not certain versions of the multiverse theory are accurate. While multiverse theories are inherently speculative, they do push the limits of our knowledge. Adams' eternal life theory pushes us to consider possibilities beyond the visible cosmos, suggesting a reality that is both vaster and more intricate than anything we could have imagined. This theory is based on the conservation of matter principle, which states that matter cannot be created or destroyed, but only transformed. This means that the atoms that comprise our bodies and everything else around us have been there since the universe began. When we die, our atoms don't just disappear. They go on a fascinating journey, becoming a part of the ecosystem and existing in different forms. This journey begins with decomposition, a natural process where microbes break down complex organic materials into simpler substances. As atoms are released, they can be taken up by plants, absorbed by the soil, and re-enter the food chain. For example, think about the life cycle of a carbon atom. After a person dies, it may be released into the soil, where it could be absorbed by a plant during photosynthesis and become an integral part of the plant. Then, when an animal eats the plant, the carbon atom becomes an integral part of the animal's body. Finally, when the animal dies, the atom is released again, continuing its journey through various forms of life. Water is just one of many examples of how one living thing can become a component of many others. The medium through which atoms travel is constantly being recycled by the environment. After we die, the water molecules in our bodies either evaporate or absorb the water from the ground, which then enters rivers, lakes, and the atmosphere. These water molecules can travel long distances, becoming a part of various ecosystems and forms of life. Similarly, nitrogen atoms, which are essential components of proteins and amino acids, are released into the environment. In the soil, nitrogen atoms are transformed into forms that plants can absorb by bacteria. Herbivores then ingest these plants, and the nitrogen atoms are recycled into new proteins in these animals. This cycle continues indefinitely, showcasing the remarkable resilience and continuity of atoms in nature. Atoms are involved in multiple geological processes, including the formation of rocks and minerals. For example, quartz, a common mineral composed of silicon and oxygen atoms in the Earth's crust, is formed by atoms. Various geological processes, such as erosion and volcanic activity, can redistribute atoms over millions of years, incorporating them into new rocks and landscapes. The subatomic particles that comprise an atom's nucleus, its protons and neutrons, also display a peculiar quality of eternal life. The strong nuclear force, one of nature's fundamental forces, holds these even smaller particles together, while atoms themselves can be broken apart. A form of permanence is suggested by the fact that, during nuclear reactions, the quarks within protons and neutrons stay bound together. On a subatomic level, electrons, which are particles that orbit the nucleus of an atom, also display remarkable stability. Under normal conditions, electrons do not decay or vanish. They can be transferred between atoms during chemical reactions, but they continue to exist indefinitely. The stability of matter is based on the enduring nature of these subatomic particles. Scientists have long been captivated by subatomic particles. One fascinating theory proposes the idea of particle-antiparticle pairs, which exist for very brief moments before annihilating each other. This phenomenon suggests that the universe is constantly being bombarded with subatomic activity, with particles being created and destroyed at an unprecedented rate, while the overall balance of matter remains unchanged. The concept of proton decay forms the basis of certain particle physics theories, which postulate that protons, which appear to be eternal on human timescales, may, in fact, decay over extremely long periods of time. If this were to be true, it would mean that not even the most basic building blocks of matter are truly eternal. Fortunately, proton decay has not been observed, and the corresponding timescales are orders of magnitude longer than the age of the universe. The fate of atoms and subatomic particles is also connected to the final destiny of the universe. In the distant future, the cosmos could go through various stages as it expands and is influenced by various forces. An extreme scenario could be the heat death of a universe, where all matter and energy are evenly distributed and thermodynamic work can't be done. In this case, atoms could disintegrate into their component parts and exist in a cold, dark universe. Another possibility is the Big Crunch, where all matter is pulled back into a hot, dense state. In this last extreme case, atoms, incineration and possible merging of subatomic particles into new types of matter is one possibility. Another is the Big Rip, in which the universe's expansion speeds up to the point that it rips galaxies, stars, planets, and even atoms apart. In any case, the basic particles would persist, though under very different circumstances than what we see today. The incredible journey of these minuscule building blocks is a reflection of the conservation of matter principle. Continually recycled through different processes, atoms undergo transformations that include becoming part of Earth's geology and constructing living organisms. The precise destiny of these particles is still up for debate, but their enduring nature highlights the continuity and interconnection of all matter in the universe. Dark matter and dark energy, two of its most enigmatic and intriguing aspects. It is believed that about 27% of the universe consists of dark matter, which is completely invisible and detectable only through its gravitational effects. Unlike normal matter, which includes atoms and everything we see, dark matter does not interact with light or any other form of electromagnetic radiation, so it is completely invisible. However, its significant roles in shaping the universe and influencing the behavior of atoms make it all the more important. It was through the gravitational influence on visible matter that scientists initially postulated the existence of dark matter. This was in response to the finding that galaxies were rotating at significantly faster rates than predicted given the amount of visible matter within them. The observed speeds could not be explained by the gravitational pull of visible matter alone, thus implying the presence of an unseen mass. One method scientists have studied dark matter is by examining the motion of stars within galaxies, but this method has its limitations. As a result of gravitational lensing, a phenomenon where light from faraway objects is bent around massive objects like galaxies, scientists are able to determine the mass of these objects. If visible matter were to predominate, the stars at the galactic periphery would orbit at significantly slower speeds than they do. On the other hand, observations reveal that these stars move at high speeds, suggesting the presence of a substantial amount of unseen matter providing the necessary gravitational pull. Galaxy clusters, which are collections of galaxies held together by gravity, exhibit a mass that exceeds that which can be explained by visible matter alone. This lends credence to the idea that dark matter exists. Despite our knowledge of its gravitational effects, the precise nature of dark matter is still unknown. Various theories have been put forth, such as weakly interacting massive particles, axions, and WIMPs, but no direct detection has been achieved. Nevertheless, experiments all over the globe are attempting to uncover it. Scientists are eager to learn more about these particles and hope that technological progress in the future will lead to more revelations. Dark energy, on the other hand, is even more enigmatic than dark matter. It is thought to comprise roughly 68% of the universe and is driving its rapid expansion. In contrast to dark matter, which draws objects together through gravity, dark energy appears to push objects apart. The idea of dark energy was first proposed in the late 1990s when scientists observed faraway supernovae, leading them to believe that the expansion of the universe would be. Contrary to expectations, the expansion of the universe was actually speeding up, which points to the presence of a repulsive force known as dark energy. The exact nature of dark energy remains a mystery, but various theories have been put forth. One theory holds that dark energy is inherent to space itself, as per Einstein's theory of general relativity. With more space comes more dark energy, which causes the expansion to accelerate. Another theory suggests that dark energy is connected to the vacuum energy, a quantum field that permeates space. However, the amount of vacuum energy predicted by quantum physics is significantly higher than what we observe, resulting in the cosmological constant problem. The coexistence of dark matter and dark energy is loaded with significance for the universe's future. If dark energy keeps driving the accelerated expansion, the cosmos could reach a point where galaxies are so far apart. Dark energy and dark matter are essential components of our cosmos. They impact the structure of the universe at large scales, but they also affect the behavior of galaxies and the formation of new ones. In one scenario, known as the Big Freeze, the universe becomes a cold, dark, and empty place. In the other, if dark energy changes over time, it could cause the expansion to become so rapid that it tears apart galaxies, stars, and even atoms. Dark matter, for example, affects galaxy formation and evolution. Without it, galaxies wouldn't have enough mass to form and stay together. Galaxies clump together and grow. This process started in the early universe, soon after the Big Bang, when dark matter clumped together due to its gravity. Studying these invisible forces is a frontier in modern astrophysics that requires innovative techniques and advanced technology. Galaxy formation of dark energy is influenced by cosmic microwave background radiation, which scientists analyze to determine the distribution of dark matter and dark energy in the universe. This radiation counteracts the pull of gravity and impacts the overall shape and destiny of the universe. As the universe expands, its influence becomes more apparent, driving galaxies further apart. Cosmology, and the search for dark matter and dark energy has persisted for billions of years. Experiments have been conducted on Earth and in space, with observatories like the James Webb Space Telescope and the Hubble Space Telescope playing critical roles in studying faraway galaxies and supernovae to deduce the effects of dark energy. Particle detectors, both on Earth and in space, are designed to directly detect dark matter particles, although these particles have not yet. Spooky action at a distance, as Albert Einstein famously called it, is one of the most fascinating and mysterious phenomena in physics. It happens when two particles become entangled to the point that the state of one particle instantly influences the state of the other, regardless of their distance from each other. To understand quantum entanglement, one must first explore the fundamentals of quantum mechanics, the branch of physics the study of the behavior of subatomic particles like electrons and atoms in the quantum world, where particles can exist in multiple states at once, a property called superposition, and where the properties of entangled particles are intertwined, meaning that the state of one particle is directly related to the state of the other. You can measure the state of one particle and instantly know the state of the other. A key experiment demonstrating quantum entanglement was carried out in the early 1980s by physicist Alan Aspect and his team. They utilized pairs of entangled photons and measured their polarization, which is the direction in which the electromagnetic waves oscillate, according to classical physics. The instant connection between the particles occurs even when they are light years apart, without any signal passing between them. This phenomenon perplexed Einstein and other physicists. The discovery of a correlation between the measurements that could not be accounted for by classical theories proved that the photons were entangled and that their states were connected regardless of their distance from each other. This finding has far-reaching implications and calls into question the long-held belief in the concept of locality, according to which objects are only affected by their immediate environment. While the speed of light is the physical limit for the transmission of information in the classical world, entanglement indicates the existence of a connection that surpasses this limitation. While this connection does not yet permit faster-than-light communication, quantum entanglement is more than just a theoretical curiosity. It has real-world applications in the new fields of quantum computing and quantum communication. When it comes to quantum computing, entanglement allows qubits to exist in multiple states at once, which means that quantum computers can process a huge amount of data more efficiently than traditional computers. One method to create highly secure communication channels using entanglement is quantum key distribution, which involves using entangled particles to generate a shared secret key between two parties. An intrusion into the communication would disrupt the entangled particles, exposing the intruder and guaranteeing the confidentiality of the transmitted data. The phenomenon of quantum entanglement also prompts philosophical inquiries regarding the essence of reality in the quantum realm. Particles in this world do not possess fixed states until they are observed, which suggests that the act of measurement itself is pivotal in establishing a system state. When Einstein, Boris Podolsky, and Nathan Rosen wanted to bring attention to the apparently paradoxical aspect of quantum entanglement, they came up with the EPR paradox thought experiment. They argued that if quantum mechanics were true, it would mean that information could travel instantaneously, which would violate the principle of locality. They believed that despite its mystique, quantum entanglement is a well-established and experimentally confirmed phenomenon. It is an essential component of the standard model of quantum mechanics, which correctly depicts the behavior of particles at the smallest scales. This was formerly believed to be an incomplete theory of mechanics, but later experiments, such as those conducted by John Bell and Alan Aspect, proved that no hidden variable theory could adequately explain the correlations observed in entangled particles. As our knowledge of the quantum world expands, researchers are delving deeper into the implications of entanglement and its possible applications. One such development is quantum teleportation, a process that uses entanglement to transfer the state of one particle to another without actually moving the particle itself. While this may not quite fit the science fiction description, it has been experimentally demonstrated. The study of quantum mechanics has led to several exciting developments in the field of quantum information science, including the development of quantum computers and other quantum technologies that rely on entanglement to function. Scientists are also looking into the potential effects of entanglement in biological systems, such as photosynthesis and bird navigation. A fascinating and challenging area of physics, quantum entanglement challenges our classical intuitions and opens up new possibilities for technology and our understanding of the universe. It has also led to new theoretical developments, such as the concept of entanglement entropy, which measures the amount of entanglement in a system. This has implications for understanding the behavior of complex quantum systems, the nature of black holes, and the information paradox. Research into this topic continues. Insights into the nature of reality and the origins of life can be gained by delving into the eerie phenomena occurring at great distances. Atoms comprise the building blocks of all things in the universe, including life. To comprehend how life came to be, one must examine the atoms and molecules that comprise living beings. The basis of life, as we know it, rests on a small number of essential elements, including carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. At the end of their life cycles, massive stars explode in supernova, scattering these elements across the universe. Stellar dust contains the raw materials for planets, and, eventually, for life on Earth, when the conditions were just right. These atoms combine in various ways to form the complex molecules needed for life. Their journey began billions of years ago in the heart of stars through nuclear fusion. Around 45 billion years ago, when our planet was still a gaseous mass left over from the sun's formation, these atoms came together to form life. At that time, Earth was being bombarded by comets and meteorites, which brought with them additional elements and water, an essential component for life. As the planet cooled, its surface solidified, and water started to accumulate in oceans. In these primordial waters, the first molecules composed of carbon and hydrogen began to take shape. The exact process by which these molecules came together to form the first living organisms remains one of science's greatest mysteries. Several theories exist, but the most widely accepted one proposes the idea of a primordial soup. This theory states that early Earth's oceans were filled with a rich mix of elements, including methane, nitrogen, oxygen, and other compounds like nucleotides and amino acids. In 1953, scientists Stanley Miller and Harold Urey recreated early Earth conditions in a lab by mixing water, methane, ammonia, and hydrogen. They then zapped the mixture with electric sparks to simulate lightning. After a week, they discovered that multiple amino acids had formed as a result of chemical reactions triggered by the sun's energy, lightning, and volcanic activity. Formed, demonstrating that the fundamental components of life could originate from straightforward chemical reactions. Once these components were in place, the following stage involved their assembly into the first primitive cells. A critical component of cells is the membrane, composed of lipids. When combined with water, lipids can spontaneously form structures called vesicles and mels, which can ensnare other molecules and create a protected environment for further chemical reactions. This process may have played a pivotal role in the DNA and RNA, the building blocks of life, interacted in ever more complex ways inside the first replicating cells. RNA, in particular, is believed to have played a pivotal role in the early stages of life because of its dual role as a genetic information store and a catalyst for chemical reactions, a function typically performed by proteins. This has led to the hypothesis of an RNA world, in which RNA molecules were the first self-replicating systems. During the process of photosynthesis, which involves converting carbon dioxide and water into glucose and oxygen, these early cells began to harness energy from their environment. This not only gave them a new source of energy, but it also increased the amount of oxygen in the Earth's atmosphere, which paved the way for the development of more complex life forms that rely on oxygen for respiration. Eventually, this led to the development of DNA and proteins. Over billions of years, these primitive single-celled creatures underwent a remarkable transformation into the wide variety of life forms we observe today. The atoms that were once part of the star now comprise every living thing on Earth, from the tiniest bacteria to the most complex multicellular creatures. The study of life's origins is not limited to gaining insight into the past. It also opens up possibilities for the search for life in other solar systems, as long as life on Earth evolved from simple chemical reactions. The search for extraterrestrial life is centered on Mars and other planets with similar conditions. Enceladus, a moon of Saturn, and Europa, a moon of Jupiter, both contain water and the chemical elements needed for life. Furthermore, understanding the origins of life has practical applications on Earth. By studying the formation and interaction of life's building blocks, scientists can develop new medical treatments and create more. We can learn a lot about the power of chemistry and the incredible potential of the elements that make up our world from studying the origins of life and the story of atoms, and how they came together to form life from the depths of the ocean to the heart of stars. This knowledge can be applied to sustainable agricultural practices, the development of new materials and technologies, and the field of synthetic biology, which focuses on designing and building new biological parts and systems. Atoms in extreme environments. As our understanding of this process grows, we come to appreciate the natural world and our role in it more fully. Atoms are the building blocks of matter, but in neutron stars and black holes, their behavior is pushed to unimaginable limits. These environments display the remarkable resilience and transformation of matter under extreme conditions. Neutron stars are extremely dense objects that form from the remnants of supernova explosions. When a star that is significantly larger than our Sun dies, its core collapses due to gravity, converting protons and electrons into neutrons. This process creates a neutron star, which is one of the densest objects in the universe. The density of neutron star material is so extreme that a sugar cube-sized piece of it would weigh. A neutron star is believed to have a thin crust of normal atomic nuclei and electrons on its surface. However, just a few hundred meters below, the pressure is so high that these nuclei are crushed together and the electrons are forced to form protons. The intense gravity on the star crushes the electrons into neutrons, which are packed so tightly that they form a superfluid. The star weighs approximately 1 billion tons. Inside the neutron star, the density grows even higher, causing the neutrons to overlap and blur their individual identities. This results in a neutron superfluid, which is remarkably stable and can conduct heat and electricity with perfect efficiency. At the center of a neutron star, conditions are even more extreme, creating a one-of-a-kind environment where matter exists in a state that cannot be found anywhere else in the universe. Black holes are formed when massive stars collapse, creating an even more extreme environment. Some theoretical models suggest that the pressure and density could be so high that neutrons break down into quarks, creating a core of quark matter that is even denser than neutron matter. Scientists are still studying these extreme conditions to better understand how matter behaves under such intense pressures. The event horizon is the boundary around a black hole where all matter, including light, is sucked in and cannot escape. At this point, the laws of physics as we know them collapse. At the singularity, in the center of a black hole, there's an infinite density and a tremendous gravitational pull. In this environment, atoms are utterly destroyed as the intense gravity compresses and stretches them. After the matter has been compressed to an unrecognizable state, it begins to spiral inward, creating an accretion disk. Within this disk, atoms undergo tremendous gravitational pull, speeding up to the point where they collide. The resulting explosions produce tremendous heat, which in turn causes the matter to emit high-energy radiation, such as X-rays. Telescopes are able to detect this radiation, which provides important insight into the behavior of matter in the vicinity of black holes. Einstein's theory of general relativity predicted that time would appear to slow down near a black hole owing to the intense gravitational field. Observations have confirmed this phenomenon, and scientists utilize advanced simulations and observations to study the behavior of black holes to better understand the extreme gravity that these objects exert. Scientific instruments such as the Hubble Space Telescope and the Chandra X-ray Observatory have provided researchers with images and data that aid in understanding the processes at work in these extreme environments. Additionally, gravitational wave detectors like LIGO have observed the mergers of neutron stars and black holes, which further shed light on these exotic objects. One of the most fascinating questions is, according to current theories, what happens to matter that falls into a black hole? It is crushed into an infinitesimally small particle. This leads us to the singularity, but there are scientists who think matter could be changed or even ejected into another universe through hypothetical structures called wormholes. These theories are still in the realm of speculation, but they are at the forefront of theoretical physics research. By studying atoms in neutron stars and black holes, we can learn how matter behaves under extreme conditions and gain insights into the laws of physics. Future missions like the James Webb Space Telescope and more advanced gravitational wave detectors promise to provide even more detailed observations. These advancements will help us uncover the secrets of neutron stars and black holes and deepen our understanding of the universe. These objects serve as natural laboratories for testing the limits of our theories and discovering new phenomena. Delving into neutron stars and black holes tests our limits of what we know and can imagine. These extreme settings test our assumptions about the universe and matter, but by studying them, we learn more about the atom's adaptability and resilience and the vast variety of the universe. As we keep exploring these cosmic frontiers, we are reminded of the infinite possibilities for scientific discovery and the eternal mystery of the cosmos. Exotic atoms are a kind of atom in which one or more of the standard part particles are replaced by other particles. A well-known example of this is the phonon, which is an unusual form of matter unlike anything we encounter in everyday life. Exotic particles are another type of exotic atom, and their discovery is one of the most fascinating and difficult topics in modern physics. The study of muonic atoms, in which a muon instead of an electron is used, enables scientists to measure the properties of the nucleus and the fundamental forces at work with great precision. Another exotic atom type is the positronium atom, which is composed of an electron and its antimatter counterpart, a positron, bound together in a miniature solar system. This atom is extremely. Due to its short half-life, positronium is unstable and annihilates itself when it comes into contact with an electron, producing gamma rays. Despite this, positronium is useful for studying antimatter interactions and antimatter properties. The search for exotic particles typically centers on those that have been predicted theoretically but have not yet been observed. The Large Hadron Collider, LHC, at CERN in Switzerland is one of the main venues for this search. The LHC is the largest and most powerful particle beam accelerator in the world. High-energy particle collisions at the LHC have the potential to recreate the conditions immediately following the Big Bang and give rise to new, exotic particles. In 2012, the LHC made a groundbreaking discovery by confirming a crucial component of the standard model of particle physics, the existence of the Higgs boson, a particle linked to the Higgs field, which is responsible for the mass of other particles. Since the standard model does not account for dark matter, dark energy, or the complete range of particle masses, it is reasonable to assume that there must be additional exotic particles beyond those already known. One such framework is supersymmetry, which states that each particle in the standard model has an entangled partner particle with different properties. These exotic particles, if discovered, could shed light on the nature of dark matter. Neutrinos, which are nearly massless and interact very weakly with matter, are another area of intense interest. Extensive searches have not yet detected any spherical particles, but the hunt is ongoing with ever more sensitive experiments. The fact that billions of neutrinos pass through our bodies every second without any discernible effect is also a mystery. Neutrino research has shown that these particles have a small mass and can oscillate between different types, or the asymmetry between matter and antimatter in the universe has long fascinated scientists. Every particle has an antimatter counterpart with the same mass but opposite charge. When these two types of matter collide, they annihilate each other, releasing energy. The apparent scarcity of antimatter in the universe is a great mystery in physics, and experiments like those at the Alpha Magnetic Resonance Observatory have helped to shed light on this mystery. I'm curious to hear your conclusion. Subscribe to the channel and inform me. The spectrometer on board the International Space Station is designed to detect antimatter in cosmic rays, which could reveal information regarding this imbalance.